Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the area of this circle. In the second question, we'll find out the area of this trapezoid ABCD. So we'll start with the first question. In the drawing, we have a circle, and we have this common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have the right triangle ACP, and side AC of the right triangle ACP cuts the circle to points A and C, and this is a right angle ACP equals to 90 degrees inside. Side CP of this right angle ACP equals to 4 units in its length. This is 970 C. This is equals to 1 unit in its length. Again, our mission is to find out the area of this circle. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, we have the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. PA equals to PB according to rule 2. But it is given as a question that PB in total equals to 4 plus 1, that is 5. So PB equals to 5. You can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. We will derive that PA is also equals to 5 units in its length. So here, PA equals to 5 units. Write it down. In the next step, I'll copy the right triangle ACP in the new page, and we'll implement the Pythagoras theorem in this right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of their produce equals to the sum of the squares of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of their produce, equals to AC squared plus CP squared. So I write it down. AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we should find out the 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and finally you get that 25 from 16 is 9, so 9 equals to AC squared. So here we take a root out of this equation, and finally you get that the length of side AC is equal to the square root of 9, that is 3. AC equals to 3 units in its length. Okay, so side AC is equals to 3 units in its length. So write it down. AC equals to 3. In the next step, we define the center of this circle. This point is point O. And we define the radius of this circle as R. In the next step, we will join points O and B together by a straight line. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and then at point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OB is the radius of the circle, that is equal to x according to our definition. So here we can implement rule 1. We'll take quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have tangent AB. This is tangent AB, that is tangent to this circle, and this point, point M. In addition, we have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OB, that is equal to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to the circle. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C here, so here the sum of the angles must be equal to 180 degrees according to rule 3, that states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have on the upper side of PB at point C? We have this angle that is a right angle, plus this missing angle. In total it must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will make a construction, that is to say, from point O, that is the center of the circle, we will make a drawing perpendicular to AC. So here, actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. So by doing this construction, we created a quadrilateral DECB. Inside created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these 4 pieces again, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, these four pieces again must be equal to 90 degrees in its size. So inside quadrilateral OECB we have four right angles. And according to rule 5, any quadrilateral that has four right angles must be at least a rectangle plus a square. So we relate to quadrilateral OECB as a rectangle because it has four right angles. So write it down. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle OECB, side OE must be equal to the opposite side BC. But BC is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the sum rectangle OECB, side OB must be equal to the opposite side EC. But OB is x, therefore EC must be also equal to x units in its length. What is the length of the missing line segment AE? From the drawing, it is very easy to see that AE equals to AC minus CC. Again, AE equals to AC minus CC. So I write it down. AE equals to AC minus EC. So AE equals to AC. AC is 3 minus EC. EC is x. So in total, A equals to 3 minus x units in its length. A equals to 3 minus x units. In the next step, we'll join points O and A together by a straight line. OA is of course the radius of this circle. This is equal to x according to our definition. So in the next step, I'll copy the right green triangle OAE in the new page, and we'll implement the Pythagoras theorem on this right green triangle OAE. Here by PT is a version for Pythagoras theorem. So this is the right green triangle OAE that is going through the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. So write it down. OA squared, that is the square of the hypotenuse, equals to AE squared plus OE squared. The hypotenuse OA is x, therefore OA squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. Plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total, we found out that x squared equals to 3 minus x squared plus 1. Here we'll open the brackets on this side of the equation, and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After I cancel x squared, on this side of the equation we will have nothing, that is to say 0, on the other side of the equation. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total, if we found out that 0 equals to 10 minus 6x. Here we'll add 6x to this equation, and we get that 6x equals to 10. Here we divide this equation by 2 and we get that 6x over 2 is 3x and this equals to 10 over 2 is 5. So 3x equals to 5. Here we divide this equation by 3 and finally we get that x equals to 5 over 3 and it's in its term. So if we found out that the radius x of this circle is equals to 5 over 3 and it's in its term. Our mission is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared. So it is known. The area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle will be equal to pi, the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the radius of our circle is equal to pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total, the area of our circle is equal to 5 over 3 squared. So it is equal to pi times 5 over 3 squared. So in total, the area of the circle equals to pi times 5 over 3 squared. 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total, if we found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So I repeat again, if we found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So we finish with the first question. In the next step, I will present you the second question and we will solve it. Our mission in this second question is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to 16, AD equals to 17, BC equals to 25, and DC equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. In general, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. And therefore, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. That is, the two parallel bases are AB and DC. That is to say, AB is parallel to DC. So the sum of the two parallel bases is AB plus DC times the height. We define the height as h divided by 2. So in total, we found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus CD, times the height. We define the height as h divided by 2. The height h must raise 90 degrees with the two parallel bases AB and DC. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is h, over 2. In order to find out the area of this trapezoid ABCD, we do a construction, that is to say, from this point A, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and DC. This point is point E. We will define the length of this line 7DE or side DE as x. And we will define the length of side AE as h. Actually, AE is equal to h is the height of trapezoid ABCD. why AE is the height of trapezoid ABCD? Because of the fact that AE is equals to x makes 90 degrees with the base DC. Therefore, AE is one side of the right triangle AED, and AE is also the height of this trapezoid ABCD. So in the next step, I'll copy the right triangle AED in a new page and we'll implement the Pythagoras theorem on this right triangle AED. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle AED that is covered from the original drawing. According to the Pythagoras theorem, in this right triangle AED, AD squared, that is the square of the hypotenuse, equals to AE squared plus DE squared. So I write it down. This will be equation 1. AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. The hypotenuse AD equals to 17 units in itself, therefore AD squared is 17 squared, that is 289, and it is equals to AE squared. AE is h, therefore E squared is h squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total we should find out that, according to equation 1, h squared plus x squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. We know that AB is parallel to DC. So those two angles are both located between the parallel lines AB and DC, and therefore they are defined as interior angles. Again, those two angles are defined as interior angles. In addition, those two angles, they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. Again, those two angles, they are both located on the right side of the straight line AE, and therefore they are defined as one-sided angles. So in total, those two angles, they are defined as one-sided interior angles. Okay. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So I'll please quickly on rule 16. According to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have line A is parallel to line B. Line I cuts the two parallel lines A and B. Those two angles, that is to say angles 4 and 5, they are defined as one-sided interangles, and therefore the sum of those two one-sided interangles is equal to 180 degrees according to this rule, rule 5. Here, angle 4 plus angle 5 equals to 180 degrees. Likewise, those two angles, this is to say angle 3 and angle 6, they are both defined as one-sided interangles, and therefore the sum of those two one-sided interangles according to this rule, rule 16, is equal to 180 degrees. Here, angle 3 plus angle 6 equals to 180 degrees. So we can actually implement rule 16 in our drawing. Why? Because in our drawing, as I already explained to you, those two angles are both defined as one-sided interangles, and therefore according to rule 16, the sum of those two angles is equal to 180 degrees. So this is a right angle, and this is the missing angle BAE. So the sum of those two angles is equal to 180 degrees according to rule 16. So I write it now. This is the missing angle BAE plus this angle that is a right angle. In total, the sum of those two angles are equal to 180 degrees according to rule 16. So I repeat again. The missing angle BAE plus the right angle, in total they must be equal to 180 degrees according to rule 16. Why? Because of the fact that those two angles, they are both defined as one-sided interangles, and the sum of two one-sided interangles is equal to 180 degrees according to rule 16. Here we subtract 90 degrees from this equation. And we get that the missing angle BAE, the size of the missing angle BAE equals to 180 degrees minus 90 degrees is 90 degrees. So if I found out that the size of the missing angle BAE is 90 degrees. So this is the missing angle BAE, that is equal to 90 degrees in its size according to rule 16. So inside quadrilateral ABFE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABFE, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at this rectangle, if not a square. So we relate to quadrilateral ABFE, it's a rectangle because it has 4 right angles. So write it down. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the sum rectangle ABFE, side AE must be equal to the opposite side FB. But AE is edge, therefore FB must be also equal to edge. What is the length of the missing line segment FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus CF. Again, FC in total equals to DC minus DE minus CF. So I write it now. FC equals to DC minus DE minus EF. So FC in total equals to DC, that is 44, minus DE, that is X, minus FE, that is 16. So in total, FC equals to 44 minus 16 is 28. So in total, this expression equals to 28 minus X. So we found out that FC equals to 28 minus x units in its length. In the next step, I'll copy the right triangle BFC in the new page and replace the Pythagoras theorem, this right triangle BFC. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to, again, BC squared equals to BF squared plus FC squared. So I write it down. BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. The length of the hypotenuse BC is 25, therefore BC squared is 25 squared, that is 625, and this is equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. In conclusion, we found out that according to equation 2, 625 equals to 8 squared plus 28 minus x squared. Here we'll open the brackets on this side of the equation, this expression, and we get that according to equation 2, 625 equals to 8 squared plus 28 minus x squared. 28 minus x squared equals to 28 squared, that is 874, plus x squared minus 2 times 28 minus x is minus 56x. So here we subtract 625 from this equation, equation 2, and we get that in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 8 squared plus x squared minus 56x, and 874 minus 625 equals to 159. Then total, according to equation 2, we found out that the 0 equals to 8 squared plus x squared minus 56x plus 159. Here we add 56x to this equation, equation 2, and we get that here 0 plus 56x is 56x equals to 8 squared plus x squared plus 159. We already found out that according to equation 1, 8 squared plus x squared equals to 289. Therefore, we can substitute 8 squared plus x squared in this equation, equation 2, by 289. We do it now, and we get that according to equation 2, $56x equals to 8 squared plus x squared is 289 according to equation 1, plus 159. So according to equation 2, we found out that 56x equals to 289 plus 159 equals to 448. So according to equation 2, 56x equals to 448. So here we divide this equation 2 by 56. We get that according to equation 2, x equals to 448 over 56. 448 over 56 equals to 8. So x equals to 8 units in itself. And found out, okay, that x equals to 8 units. Our mission is to find out the area of this trapezoid ABCD. And we already found out that the area of trapezoid ABCD is equal to the sum of the two parallel faces, that is actually AB plus CD times the height, that is h, over 2. So the area of trapezoid ABCD is equal to AB, that is 16, plus CD, that is 44, times the height h over 2. So actually we have to find out the height of trapezoid ABCD. According to equation 1, h squared plus x squared equals to 289. We found out that x equals to 8. If x equals to 8, it means that x squared equals to 8 squared, that is 64. So we can substitute x squared in this equation 1, equation 1 by 64. We do it now and we get that according to equation 1, 8 squared plus x squared, that is 64, equals to 289. Here we subtract 64 from this equation 1, and we get that according to equation 1, 8 squared equals to 289 minus 64 equals to 225. So if we found out that 8 squared equals to 225, here we take a root out of this equation, and finally we get that h equals to the square root of 225, that is 15. So if we found out that h equals to 15 units in itself. So here h equals to 15. So the total area of trapezoid ABCD equals to 16 plus 44 is 60 over 2 times h, that is 15. 60 over 2 is 30. So in total this expression equals to 30 times 15. 30 times 15 is 450. So in conclusion, if we found out that the area of this trapezoid ABCD is equal to 450 square units. And that is the answer to the question. Repeat again, the area of this trapezoid ABCD is equal to 450 square units. We finish with the second question. In the next step, I summarize the lecture. We start with the first question, of course. In the first question, our mission is to find out the area of this circle. So in the drawing we have a circle, and this is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have the right angle ACP that cuts the circle at 2 points. Point A in this point. This angle ACP is the right angle. We know that side CP for the right angle ACP equals to 4 units in itself. This is line segment BC, that equals to 1 unit. Again, our mission is to find out the area of this circle. So here, we implemented rule 2. For the common sum point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule 2, they are equal to each other. That is to say, PA equals to PB. Okay, again, if we found out that according to rule 2, PA equals to PB. But it is given as a question that PB in total equals to 4 plus 1, that is 5. So we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we will derive that PA also equals to 5 units in its name. PA equals to 5. In the next step, I copied the right triangle ACP in the new page and implemented the Pythagoras theorem. This right triangle, triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. So this is the right triangle ACP, that I forward from the original drawing. This right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. 8p is 5, therefore p squared is 5 squared, that is 25, and it is equal to AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. In total, we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and finally found out that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we took out of this equation, and finally found out that the length of the ellipse inside AC is equals to the square root of 9, that is 3. So AC equals to 3 units in its length. So this is side AC, that is equals to 3 units in its length. AC equals to 3. In the next step, we define the center of this circle. This point is point O. We also define the radius of this circle as x. In the next step, we join points O and B together by a straight line. OB is of course the radius of the circle, that is equals to x according to our definition. Here we implemented rule 1. We have the radius of B, that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given as a question that PB is a tangent. So PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to the rule that states that the sum of the angles on the upper side of the straight line is equal to 180 degrees. Okay, so which angles we have at the upper side of the straight line PB at point C? We have this angle that is a right angle plus this missing angle, in total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say from this point O, that is the center of the circle, we do perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point T. By doing this construction, we created the quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 rectangles. And according to rule 5, that said that any quadrilateral that has 4 rectangles must be this rectangle, if not a square. So we relate to quadrilateral OECB is a rectangle because it has 4 rectangles. But we also know that opposite sides of a rectangle are equal to each other. So an rectangle OECB, side OE must be equal to the opposite side CB. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB is equal to the opposite side EC. But OB is x, therefore EC must be also equal to x units in its length. What is the length of the missing line segment AE? AE equals to AC minus CC. Again, AE equals to AC minus CC. So AE equals to AC, that is 3, minus CC, that is x. So in total, AE equals to 3 minus x. In the next step, I join points O and A together by straight line. OA is the radius of the circle, that is equal to x. In the next step, I copy the right triangle OAE in the equation to implement the Pythagoras theorem in this right triangle OAE. Okay, this is the right triangle OAE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. OA is 1, therefore OE squared is OA is x, therefore OA squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we shall find out that x squared equals to 3 minus x squared plus 1. Here we open the brackets of this expression and find out that x squared equals to 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel x squared, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation, we have 9 plus 1, that is 10, minus 6x. So in total we shall find out that 0 equals to 10 minus 6x. Here we added 6x to this equation and found out that 6x equals to 10. Here we divided this equation by 2. So 6x over 2 is 3x and 10 over 2 is 5. So in total we found out that 3x equals to 5. Here we divided this equation by 3 and found out that x equals to 5 over 3 units instead. So we found out that the radius of this circle x equals to 5 over 3 units. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. But again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle will be equal to pi times the radius of our circle squared. The radius of the circle is x, therefore the radius squared is x squared. So in total, we found out that the area of our circle equals to pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. Therefore, in total, we found out that the area of our circle is equal to pi times 5 over 3 squared. So it is pi times 5 over 3 squared. 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area of this circle is equal to either 25 pi over 9 square units. So in terms of numbers, the area of this circle is equal to 8.727 square units. We finished with the first question. In the next step, I actually presented to you the second question and we solved it. In this question, our mission is to find out the area of this trapezoid ABCD. Actually, it is given us the question that AB equals to 16, AD equals to 17, BC equals to 25, and DC equals to 44. Again, our mission is to find out the area of this trapezoid ABCD. Actually, the area of any trapezoid equals to the sum of its two parallel bases times the height over 2. And therefore, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually AB plus DC, because AB is parallel to DC. So it is AB plus DC times the height, that is h over 2. So there are our trapezoid ABCD equals to the sum of its two parallel bases, that is AB plus CD, times the height, that is h over 2. The height h must create 90 degrees with the two bases AB and DC. In order to find out the area of this trapezoid ABCD, we did a construction. That is to say, from point A, we drew perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. Likewise, we defined the length of this line 7DE or side DE is x. We define the length of side AE is h. AE, that is equal to h according to our definition. AE is also the height of trapezoid ABCD. Why AE is the height? Because of the fact that AE creates 90 degrees with the base DC. So AE is both the one side of the right triangle ADE, and AE is also the height of this trapezoid ABCD. So in the next step, I copied the right triangle ADE in a new page and implemented the Pythagoras theorem in this right triangle ADE. So this is the right triangle ADE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ADE, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. AD squared equals to A squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, plus AE squared. AE is 8, therefore A squared is 8 squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total, according to equation 1, we found out that 289 equals to h squared plus x squared. In the next step, we did another construction, that is to say, from this point B, we draw perpendicular on DC. Again, from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. So here, we know that AB is parallel to DC. So those two angles, they are located between the parallel lines AB and DC, and therefore they are defined as an interior angles. And those two, in addition, those two angles, they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles, they are defined as one-sided interior angles. According to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So the sum of those two angles is equal to 180 degrees according to rule 16. So this is the missing angle, that is angle BAE, plus this angle, that is the right angle according to our construction. In total, the sum of those two angles is equal to 180 degrees according to rule 16. So if we again, according to rule 16, the missing angle BAE plus the other angle, that is the right angle, in total the sum of those two angles must be equal to 180 degrees according to rule 16. Why? Because of the fact that those two angles are both one-sided interior angles, and according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So here we subtract 90 degrees from this equation, and finally found out that the missing angle BAE equals to 180 degrees minus 90 degrees is 90 degrees, of course. So the missing angle BAE equals to 90 degrees in its size. This is the missing angle BAE that is equals to 90 degrees in its size. So actually found out that inside quadrilateral ABFE we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABFE we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must meet its rectangle not a square. So we relate to quadrilateral ABFE is a rectangle because it has 4 right angles. If quadrilateral ABFE is a rectangle, according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the sum rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is H, therefore FB must be also equal to H. So, what is the length of the missing line segment FC? From the moment, it is very easy to see that FC in total equals to DC minus DE minus CF. Again, FC equals to DC minus DE minus CF. Here, FC equals to DC minus DE minus CF. So FC equals to DC, that is 44, minus DE, that is X, minus FE, that is 16. So in total, FC equals to 44 minus 16 minus X. 44 minus 16 is 28. So FC in total equals to 28 minus X. FC equals to 28 minus X. In the next step, I copied the right triangle BFC in a new page and implemented the Pythagoras theorem in this right triangle, triangle BFC. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. BC is 25. Therefore, BC squared is 25 squared, that is 625, and this is equals to BF squared. BF is X, therefore BF squared is X squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total, according to equation 2, we have found out that 625 equals to H squared plus 28 minus X squared. So here open the brackets of this expression, and I should have found out that 625 equals to h squared plus 28 times x squared. 28 times x squared equals to 28 squared, that is 874, plus x squared minus 2 times 28 times x, that is minus 56x. So here we subtract 625 from this equation. Equation 2, so in the side of the equation we left with nothing, that is to say 0, and in the other side of the equation we have x squared plus x squared, x squared plus x squared, minus 56x, and 874 minus 625 is equal to 159. So in total, according to equation 2, we have found out that 0 equals to x squared plus x squared minus 56x plus 159. Here we added 56x to this equation, equation 2, and finally found out that 56x equals to h squared plus x squared plus 159. According to equation 1, h squared plus x squared equals to 289. So we substitute x squared plus x squared in this equation, equation 2, by 289. And we found out that 56 equals to 289 plus 159. 289 plus 159 is 448. So in total, according to equation 2, we found out that 56x equals to 448. So here we divided this equation 2, by 56, and finally found out that x equals to 448 over 56. So 448 over 56 is 8. So we found out that x equals to 8 units in its length. And according to equation 1, x squared plus x squared equals to 289. But we only found out that x equals to 8. If x equals to 8, it means that x squared equals to 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We did it, and we found out that 8 squared plus x squared, that is 64, equals to 289. Here we subtract 64 from this equation 1, and found out that 8 squared equals to 289 minus 64 is 225. So x squared equals to 225 according to equation 1. We took out of this equation and found out that h, that is the height of trapezoid ABCD, is equal to 15 units. Our mission is to find out the area of this trapezoid ABCD. We only found out that the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC times the height, that is h over 2. And again, we already found out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus CD times the height, that is h over 2. Just like now found out that h equals to 15. So the area of trapezoid ABCD in total is equal to AB, that is 16, plus CD, that is 44, times the height h over 2. 16 plus 44 is 60, divided by 2, times the height h, that is 15. So in total, the area of trapezoid ABCD is equal to 60 times 15 over 2. 60 over 2 is 30. So in total, this expression equals to 30 times 15. 30 times 15 is 450. So in total, we found out that the area of this trapezoid ABCD is equal to 450 square units. Okay? Thank you very much.